6.2. Characteristics of the equations of polynomial functions. I'm just going to go through a whole bunch of examples here. You'll notice that on this page we have a linear example, we have a quadratic example, and we have a cubic example. So we're going to go through each one of these examples and determine the type, the number of possible x-intercepts, or in this specific case, we also want to identify how many intercepts there actually are. We want to identify what the y-intercept is, not the number of y-intercepts, because we've noticed from our past note, from our past set of notes, that there will always be one. So we want to identify what that y-intercept is. We want to identify the end behavior, the domain of each function, the range, and the number of possible turning points. And just like in this, in the x-intercepts, we want to determine how many there actually are in each one of these. So let's start off with this one. So if we look at the type, we can see that this is a linear, because the implied exponent on this x is simply 1. So that's how we know that it's linear. There's not x squared or x cubed, there's just x. So the number of possible x-intercepts in a line is always going to be 1. And just to prove it, let's graph it. So we're going to clear this one from the last notes. We're going to say 3x minus 5. Graph it. And lo and behold, right here, this right here is our x-intercept. The y-intercept, that's always going to be identified by our constant term. So it's going to be at negative 5. But let's just negative 5. Let's just look at the graph itself. So when I go second trace, and I want to find the value at x equals 0, enter. I'm noticing right here that when x equals 0, that's where the y-intercept is. Y equals negative 5. That's true. Now let's talk about the end behavior. We're noticing that if this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4, we're saying that it's going from quadrant 3 to quadrant 1. I'm just going to simplify it by calling it EB. I'm going to say quadrant 3 to quadrant 1. And we know this because the leading coefficient is positive. If it were negative, that means that it would go from, let's look at this, it would go from the quadrant 2 to quadrant 4. The domain of lines is always going to be every single x value. So x such that x is an element of the reals. Our range is very similar, but we're going to say y such that y is an element of the reals. That's all. When we say x is an element of the reals or the y is an element of the reals, it just means that for this function, you can have any x value and you can have any y value. And the number of possible turning points is going to be 0, because it never goes from an increasing to a decreasing. It's always simply increasing. Let's look at this one here. We know the type. It's going to be quadratic because we have that greatest exponent is going to be a 2. So we have a quadratic. That's going to be our parabola. the number of possible x-intercepts. With a parabola, it's always going to be 0, 1, or 2. But let's graph this thing to see how many actual x-intercepts there are. So I'm going to go into my graphs. I'm going to say clear. I'm going to say negative 2x squared. And you might want to type this in alongside with me. Pause it and type it along with me just to get your fingers used to it. Minus 4x plus 8. I'll graph this thing. And look at that. In this case, we have it opens down and we have 2. So I'm just going to highlight the fact that, yeah, in this case there are actually 2. The number of possible could be 0, 1, or 2, but in this one it is simply 2. The x-intercept, sorry, the y-intercept, remember that's going to always be given by our constant term. So we're going to have the x-intercept is at positive 8, but let's just double check here. So I'm going to go second trace. I'm going to find out the value. Value in x equals 0. And look at that. When x equals 0, y equals 8. So we're good. After that, we have end behavior. We're noticing that it's going from quadrant 3 to quadrant 4. And this is because the leading coefficient is negative. If it were positive, we would have a parabola that opens up, and so it would be going from quadrant 1 to quadrant 2. However, in this one, we're going from quadrant 3 to quadrant 4. And this is because the leading coefficient is negative. The domain for parabolas is always x, such that x is an element of the reals. Because when we look at it, we can see we can cover every single x value. So this extends beyond here, so it goes all the way out to infinity, and negative infinity, and to positive infinity. The range is a little bit different. We're noticing that we have a minimum here. So what I'm going to do, just so that I can see the vertex, or right here, this turning point, or another way that we can call it in this one is the maximum, I'm going to go second trace, and I'm going to go to the maximum. Enter. I'm going to go to the left of it, the left bound. I'm going to scroll over here to right of it, and enter. We know that the maximum occurs when x equals negative 1, but the maximum that y can be is 10. So the way that I would write this is I would say y such that y is less than or equal to 10. Y is an element of the reals. So it can be anything as long as it is less than 10. Because if it's greater than 10, it'll be all the way up here. Okay? And there's nothing happening up here in the graph, just everything below. Last but not least, we have our turning points, so a number of possible turning points. In a quadratic, it's always going to be 1. Good. Last but not least, let's talk about this cubic. So the type is going to be cubic. And we know that because the greatest exponent in the equation is 3. The number of possible x-intercepts, where the graph intersects with the x-axis, it can be as, no, it's always going to be more than 1. It's going to be 1, 2, or 3. So let's see which one it actually is. I'm going to go into my graphs, and I'm going to say 2x. Now this is a little bit different. We have to put the petit chapeau. X to the power of 3 plus 10x, and there's a special little button here for the squared, so squared, minus 2x minus 10. Graph this thing. Woo! Look at that. So the number of times this graph touches the x-axis is 1, 2, 3. So in this case, we're going to say that there are 3 x-intercepts. The y-intercept, remember it always occurs where the constant term is, so that's going to be at negative 10. Don't take my word for it, let's check it out. So I'm going to go second trace, I'm going to hit the value. When x equals 0, what does y equal? Look at that, negative 10. That's where it touches right down here. The end behavior, it's going from quadrant 3 to quadrant 1. That's because the leading coefficient is positive 2. If it were negative, let's just do a little bit of an experiment here. If I were to insert a negative right here, we'll see the leading coefficient, which is the coefficient that's in front of the variable with the largest power. When I do that, hey-o, it goes from quadrant 2 to quadrant 4. So let's just delete that to get our original function back. Good. The domain for cubics is always going to be x such that x is an element of the reals, because x can be anything. The range is also the same, only with our y. Y such that y is an element of the reals. And the number of possible turning points is going to be 0 or 2. Let's just look to see what's the case here. Now my gut is saying it's 2 because I know that it goes up here, but let's change the window settings just a little bit. So I'm going to make my y maximum right here because it kind of goes off the charts here. I'm going to make that 50 and just we'll see. Look at that. Turning point here, turning point here. So the turning points is actually for this specific one is going to be 2.